excited about it. So for some brief context, I've been working on the JAX team not too long, and before that, I worked on TensorFlow Probability, which is essentially a probabilistic programming framework built on top of TensorFlow and JAX. So as someone new to the JAX team and kind of learning about it, I figured I'd kind of bridge the gap between JAX as like a library for differentiable programming to my previous work, which is Oryx, which is a library for probabilistic programming. The title.
Sorry for the interruption.
Yes.
Do you want to share your slides?
Yes, I'm about to. So as a brief overview of the talk, I don't have very many slides. So a heads up, there's going to be a lot of coding in this talk, live coding. So let's hope that goes well. But the basic premise of this talk is going to be about Jaxpr, which is JAX's internal representation. You can see here we have it at the center, and around it are kind of a sea of community-driven projects that use Jaxpr instead of JAX directly. And this was not intentional on the part of JAX. JAX was originally designed for AutoGrad and kind of staging out to accelerators, but these projects have taken the internal representation that JAX used and used it in a whole different way. So basically in this talk, I'll be both teaching you about Jaxpr and highlighting Oryx, which is essentially the probabilistic programming framework that builds on top of Jaxpr as an internal representation. So a really quick overview of JAX. So JAX is one slide. Basically, JAX is a Python library for numerical computing. The important bits are that it exposes program transformations. So you write your Python code, it's essentially regular NumPy, and then you can essentially transform the functions you wrote with JAX provided higher order functions. And these things do things like JIT compiling your code for accelerators and auto differentiation via CRAD. So that's the whirlwind tour of JAX. I'll jump right into some live coding. And let me know if you can see this all right, because I'm going to switch windows. Can you see this all right?
Yeah, it works.
It's good.
Cool. So first, I'll talk about Jaxpr. So I'll write a new file called what is Jaxpr, and I will run it here on the side. Sorry, there might be some typos and whatnot because this is live coding. And the entire point of this is I want to demonstrate how accessible Jaxpr is and why it's kind of spawned off this big community of people who use it for various cool things in the numerical computing world. So I'll import Jax, and I'll import Jax's wrapped NumPy. And I'll write a really simple function. So this one will just take x. We'll take the sine of x. We'll take the exp of y, and then we'll turn the cosine of z. Really simple function, and in JAX, we can just run it, as we're just applying a series of operations to 2. And you can see here, it spits out a value. So what's so special about this? We're just eagerly executing this just NumPy. But what JAX does is it provides a way to stage out this Python code into our internal representation very easily. So instead of saying f of 2, I'll say jax.make Jaxpr of f of 2. And you can take a look at JAX's internal representation, and it's here on the right. And this is what we call a Jaxpr. It's essentially an anormal form. You can see here that we've essentially annotated each of the intermediate variables with types, which we essentially infer, and it's built via tracing. So instead of passing in 2 into f, we'll pass a dummy object, a tracer into f, and instead of applying the operations, it'll record them and build up this data structure. So the important bits in Jaxpr are the invars, or the inputs to it. And let me show you a quick little tweak. So I'll change this to a vector rather than a scalar, and we'll see all the types update. You can see here that they're now vector types instead of scalar types. So each Jaxpr has all the types, the shapes baked into it a priori. So we'll take our inputs and we'll apply a series of equations to them. And each equation is a set of inputs, which are on the right. You can see sine A. It's a primitive, which these are essentially the base ops in JAX, and an output. And the basic idea is that every time you apply primitive, you read the inputs from the set of previous variables. You apply the primitive and you write it to a new variable. And at the end, you return an output. So it's a dead simple IR. And my favorite part about it is that it's accessible, and you can essentially do whatever you want with it from Python. So I could say Jaxpr equals makes Jaxpr, and then I could say print Jaxpr.equations. So But now I'm actually printing out the equations of the Jaxpr, which are just a Python data structure. So the fact that it's accessible in Python makes it really hackable, makes it really easy to understand and introspect, and makes it really a really good candidate for essentially building your own Jaxpr transformations, essentially. So what does JAX do with Jaxpr? So Jaxprs weren't originally designed to be a general purpose IR. They're actually pretty specialized. Specifically, they're good for tensor array programming, if you will, TensorFlow, PyTorch, these sorts of applications, which basically boil down to two things. The first is automatic differentiation. So, I can take f and I can say jax.grad of f of 2, and it'll print out some scalar, which is the gradient of f. And what JAX is doing internally is it's tracing out f into a Jaxpr, applying some special rules for each primitive, and then interpreting that Jaxpr backwards to do the backwards pass, as in backpropagation. And the second thing that JAX does is that it can JIT compile your function for accelerators like CPU, GPU, TPU. So if I say jax.jit of f2, it doesn't really change anything about the function, but it does lower it to a lower level representation that can then be used by a compiler. So in this case, I could say .lower a compiler IR, and you can say take a look at the internal representation that, say, JAX uses, and I'll try a range just to make it a little bit more interesting. Yeah, you can see here that JAX internally translates the Jaxpr into essentially an LLVM like IR right here. So that's actually basically all I'm going to tell you about Jaxpr. It's not very complicated. There are more things I'm not mentioning, but for the purposes of this talk and understanding why Jaxprs are powerful, I think I've basically said all I've needed to say. So the next thing we're going to do is we're going to write our own Jaxpr interpreter. So what does that mean? It's basically a way of consuming this Jaxpr data structure, and we're going to do it in a special way. So we'll write a new file called mini-inverse. And I will run it. So we'll import JAX as before. We'll import JAX.numpy as before. And I'll copy over my function and the fact that I'm creating a Jaxpr from it. So what can we do with Jaxprs? The simplest thing we can do is we can interpret them forward, as in just evaluate the Jaxpr. And that'll be our starting point for this interpreter. So I'll write a function eval Jaxpr. I'll take in a Jaxpr and an input. And for the purposes of this talk, I'll assume that the Jaxpr we're working with has one input, one output, and the primitives we're working with also have one input, one output, but this could easily be generalized to variadic Jaxprs and primitives. So what exactly does it mean to eval a Jaxpr? It's just evaluating essentially in a normal form, like programming language. So what we'll first do is we'll set up an environment, and this will map the intermediate variables in the Jaxpr to values. Write a little helper function readenv, and it'll take in a variable, and it'll just look up the value of that variable in the environment. And then we'll do write-env. It'll take a variable and a value, and it'll just write that variable, write that value to that variable. And that's basically a great starting point. We'll initialize our interpreter by writing jaxpr.invar0 and val. So that'll essentially say A is going to be some value. The next thing we'll do is we'll loop through the Jaxpr equations. And for each equation, we essentially want to read its input from the environment, apply the equation, and then write its output back into the environment. So we'll say equation input equals readenv equation.invar0. Equation output equals equation.primitive.bind. And bind is essentially how you call a primitive. So we're essentially executing sign on A, basically. And then write-env equation.outvar0 and equation output. So what we're doing is we're looping through all the equations and essentially populating this environment. And just as a quick test, I'll print out the environment at the end, just so you can see essentially what's happening underneath the hood. So I'll call it eval Jaxpr, Jaxpr, and 2, and see if and pray that everything works. All right, yeah, looks like it worked. You can see here that we print out a dictionary. A is set to 2, which is our initial value. B has this value, which is essentially the sign of A, and then C and D, et cetera, have all our values. So the last thing we need to do is return the output of the Jaxpr. So we just say return readen Jaxpr.outVar 0, and that's it. So now we can say print eval Jaxpr, and should match the same value as before, as in print f of 2. So we've not really done anything here. We've just staged our Python function out into a Jaxpr, and we've reinterpreted the Jaxpr. So we should be doing exactly what we did in Python in the first place, but I'll switch it up a little bit. Let's now try to write an inverse interpreter. So it'll take the output of the function and try to compute the input. And obviously this is hard to do in general. So because I've kind of constrained the function to be a unary function with unary primitives, this actually won't be too bad. So the first thing we'll do is we'll change our function to eval Jaxpr inverse. So inputs, we'll get outputs. The environment will stay the same. We'll just have something to read and write values to. Instead of writing the Jaxpr.invars, we'll write the outvars. So you can imagine we're starting with D here. So we're writing D to the environment. Instead of interpreting the equations forward, we'll reverse the list and interpret the equations backwards. The equation inputs will become equation outputs, and the invars will become outvars. I'll handle this in a second. But we essentially want to compute the equation's input, and then we'll write the equation's invar, the essentially expected input to that function. And finally, we'll read Jaxpr.invar 0. So we've just reversed this interpreter. So what do we do here? We're writing our own custom interpreter. So we actually have to write our own rules for the primitives. So every time we see an exp, we'd have to apply a log. That's essentially the inverse. And anytime we see a sign, we'd want to apply arc sign. So we'll create a dictionary that contains these rules. And we'll say, OK, for sign, and that's stored somewhere in Jax. It's a primitive inside of Jax, so I can kind of pull it out. I'll say it's essentially jnp.arcsign. And for cosine, it'll be jnp.arccosine. And for exp, it'll be log. So we set up all our rules. Now let's apply them. So we'll look up the primitive in the registry and apply it to equation output. And fingers crossed, I think this should work. It's a very small modification to our previous interpreter, but let's say we pass in f applied on point 2. So we're essentially hoping that the inverse cancels out the f essentially, and we get point 2 out. We do. We can say that inverse here, essentially f inverse of f of point 2 gives you point 2. So this is essentially baby's first Jaxpr interpreter. And all we're doing is we're consuming this Python data structure and doing something unique with it. And a second point I want to make about Jaxprs and Jax as like a flexible, simple, extensible system is that we've worked with existing Jax primitives like sine, cosine, and exponent, but you can actually add your own primitives into the system without too much effort. So I'll do that right now. So let's say I want to add in a new primitive called add1. Do that by just constructing this primitive. And the two main things we need for this primitive are essentially its implementation, how do you evaluate forward, and what you call an abstract eval rule. And that's essentially how do you evaluate it on an abstracted value like these shapes here in the Jaxpr. So I'll do that real quick. So add1 p.def impl on the x plus 1. That's easy enough. And then the def abstract eval rule. This will taking an eval, an abstract value, and it'll essentially return abstracted value out. And in Jax, we have shaped arrays. That's basically just saying it's a value with a shape and a d type. And because we're adding 1 to it, we're not really changing it. So yeah, that's just the abstract eval rule. It just returns something of the same shape and d type. And we could say print, let's write a new function, g of x, and return add1 p.bind of f of x. And we can now print this in Jaxpr form. And you'll see that it'll be the exact same Jaxpr as before, but we'll now have this add1 there. So to finish adding this new primitive into the system, we'll want to add an inverse rule for it so we can invert it. So we'll say inverse registry of add 1p equals lambda x minus 1. And now we can actually say, we can now essentially do the same thing we did before, where we eval Jaxpr inverse, but we'll use the new Jaxpr, and we'll ask it to invert g of 0.2, which is the function, and you see we get a 0.2 again. So basically, the two aspects of extending Jax are adding your own custom transformations via these Jaxpr interpreters, and adding new primitives via essentially Jax core primitive. And these are the two ideas that Oryx uses for probabilistic programming. So I'll now briefly transition into Oryx and hopefully cover some interesting things that you can do in probabilistic programming with Jaxprs. So I'll write a new file, what is oryx.py, and change to that. So why did we talk about inverse? Well, it's because Oryx actually has its own inverse. So if I were to say or to copy my function f from here, we do the same Jax imports. I can essentially do oryx.core.inverse f of 0.2. And Oryx will essentially do the same thing, but it's slightly more advanced. I just want to demonstrate this one interesting aspect of Oryx's inverse, where if you have a function of two variables, and you say jnp.sine of x and x times jnp.x but y. We assumed unary functions before. Now there's a little bit more advanced. Oryx can actually invert this as well. You can see right here that Oryx was able to successfully invert this function. And this is a little bit more complicated because you have to first invert the sine part to obtain x, and then you have to run this forward to divide by x to invert after you take the log of it to get y. So there's a little bit more going on here. So Oryx obviously has done a little bit more work than just going backwards, but fundamentally it's just another Jaxpr interpreter. And why do we care about inverse for probabilistic programming? Well, let's first talk about what a probabilistic program looks like in Oryx. And the basic idea is that Oryx adds new primitives to the system that represent sampling random variables. So we can essentially add one right now. So we'll say random normal p equals jax.core.primitive, random normal. And we'll give it an impl rule that takes in a source of randomness, a key in Jax, and just samples a random normal from it. So this is just the forward evaluation rule. It doesn't have to be that complicated. And you can see that if we call this find, it should just evaluate to some random number, -0.2. And if I change the key, it'll give me some other number. So what's the point of writing your own random normal primitive? Well, in Oryx, let's say we wrote a program like this. Takes in a key, and it says return random normal p.bind of key. And the idea is that we can do crazy things in this program. I could say give it x and then multiply it by x, or maybe I want to wrap this all in a jnp.x or something. You can write really complex probabilistic programs just because they look like Python functions that Jax knows how to handle. Like I could JIT this function, I could take grad with respect to x. There's something super special about this function. The point is that we can stage it out to a Jaxpr, and Oryx can reinterpret that Jaxpr in interesting ways. Specifically, we want to do the basic probabilistic programming idea of taking something that's written for sampling and converting it into something that computes log densities. And Oryx has a transformation for that called logprob. So I will quickly import that, and also I'll import like a very simple normal distribution, so I don't have to compute log probs manually. Right, so back to our program. Let's start off with the simplest program, random normal p bind. So this is a program that just samples a real valued number. And what we'd like to do is we'd like to convert it into one where I give it a real number and it'll tell me what's the probability you sampled it from this program, or what's the density of that real value in this program. And we can do that via the log prob interpreter, but random normal is a primitive we wrote, so we have to register a log prob rule with Oryx for this random normal primitive. And I'll do that real quick. So def random normal log prob rule. And as I described, the Oryx's inverse transformation is a little bit more complicated than the one we wrote in the previous file. It actually does some forward and backward sort of propagation of information. And the log prob actually works similarly, and it'll soon be clear why. So the rule won't be as simple as some lambda, but I'll write it out and try to explain the components. So instead of being passed in values, we'll essentially be given the inputs and outputs to this primitive, which in the inputs would be the key and the outputs would be the value that we sampled from this primitive. There'll only be one, so we can essentially, there'll only be one, so we'll throw away the rest of the out cells, and we actually don't really care about in cells. And the one thing we need to check is that the output value is ready. Because there's this complicated propagation of information happening in Oryx's inverse, this rule may be executed before out cell is actually ready to compute the log density. So essentially, I'll write a little check for that. If it is ready, we can extract the value, which is essentially the output of the random normal p. And then we return in cells, out cells, pfd.normal log prob of val. So basically this says if the value is ready or not ready, don't do anything. If it is ready, we return, instead of none, we return the actual log probability of this value. And then the last thing we could do would be actually add the rule. And that registers our own primitives rule in Oryx's custom transformation. And the final thing is now to apply it. So we wrote our program up here. Let me move it a little bit further down. So you can see, if we look at the Jaxpr of this program, it won't look anything special. It'll just be a single call to forgot to define my abstract eval rule. Let me do that real quick. It's just sampling a scalar. So I'll just return a jax.core.shape array that has scalar shape. And we'll see here that we have it now in a Jaxpr. It takes in this key, this U32.2. That key is consumed by random normal, and then we return a scalar. Finally, we call the log prob transformation. So what's the log prob of sampling 0 from this program? And it should spit out a number. I'm sure you all have seen this number 1,000 times. It's the probability of sampling 0, or the density of log density of sampling 0 from a 0-1 Gaussian. And this is not super special. It's a really simple program, but let's tie it back to inverse. So what happens if I were to say, okay, let's say I sampled x, then instead of returning x, I return JNP of x of x. So what I've done is I've taken my random variable and I've transformed it with essentially an invertible transformation. And this essentially, instead of just taking log prob of x, we need to actually use the change of variable formula, which involves both inverting this function here and accumulating a volume change correction. So Oryx's log prob actually does that as well, and that's why inverse is important for this. It actually walks the Jaxpr back up. Let me change that real quick. So it actually walks the Jaxpr back up. You can see here the Jaxpr now has an x in it, and it tries to essentially figure out what b is. It knows that random normal is a special sampling statement, but it has to invert everything else so we can obtain b, and also keep track of the volume change along the way. And now essentially we have a log normal log PDF instead of our normal PDF. And we can do essentially whatever we want with this, as long as we transform it with invertible operations that have tractable inverse log Jacobians. And this is essentially the entire pitch of Oryx, or at least it's one of the things it can do. It takes these Jaxprs, it embeds sampling statements in them as primitives, and then is able to transform them via custom interpreters on Jaxpr. I guess that's, there's actually, I guess the nice thing about this is that we have this now log-prob transformation. It turns a sampling program into a log density program. It actually nicely fits in with the rest of Jax's system. So I said Jax is a library mainly for auto differentiation and staging out to compilers. So what happens when we try using them together? So one thing that's pretty normal to do, for example, in MCMC algorithms, Hamiltonian Monte Carlo, is we like the gradient of the log prob with respect to a set of samples. So if we had this function right here, we could essentially just wrap this in jax.grad. And what jax.grad will do is it'll retrace this function into a Jaxpr. So it'll trace the log prob of program into a Jaxpr, and it'll take the gradient, it'll interpret that backwards to complete the gradient. So what we're doing is we're nesting Jaxpr transformations inside each other, which is really what makes the complexity of the system blow up. We really can express a lot. And you can see here that we got the -0.5. And this is essentially the building block of algorithms like HMC, where we can now build efficient samplers for distributions that are potentially written in pretty complex ways. And another example would be taking gradients direct to essentially parameters in the distribution. So I said, okay, I write a program that takes in an additional input W, and all it does is add W to the output. We can now say, okay, let's say I observe some data like 50. How can I maximize the likelihood of observing that data? And you can do that with jax.grad of jax.log prob as well, except instead of taking the gradient with respect to the first argument, we take it with respect to the second argument, which is W. We say, where is W pointing me to maximize the likelihood of this data? Let's say the data we observe is 4 and W's initial value is 0. We expect to see a gradient that essentially points you in the upper direction, in the positive direction. And yeah, you can see here there's a little gradient pointing W to increase to maximize the likelihood of seeing 4. And this is the building block of algorithms like variational inference and normalizing flows, which essentially are these maximum likelihood algorithms, or elbow maximization algorithms in the case of variational inference. So what I've done is I've kind of like peeled back the hood on Jax a little bit so you can see what's happening underneath the hood and how it's really easy to extend the system to do some pretty interesting and complicated things, especially for probabilistic programming. And for Oryx, this is also the tip of the iceberg. Logprob is just one of several transformations inside of Oryx. Oryx also has transformations that enable manipulating probabilistic programs, like sampling joint distributions and computing joint log probabilities and intervening on certain random variables. It also has a pattern matching system where you can take these Jaxprs and run kind of sophisticated pattern matching on them for things like automatic marginalization. There's an autoconj paper that is currently being implemented in Oryx. And it also has neural network components as well. It said neural PPLs in the title slide. Oryx also supports things like deep generative models where you have neural networks embedded inside of your probabilistic models. And all these transformations also like seamlessly integrate into the Jax system as well. So I guess I'm almost out of time, and I probably have time for like a question or two, but the main takeaway is that we use a really simple IR. It's embedded, it's specifically hackable in Python. Most of Jax users are using Python, so this makes it really accessible to them. And it's simple enough to extend that you can do things that the original Jax creators never dreamed possible, including probabilistic programming. And yeah, that's basically all I have to share today.
Cool. Thanks a lot for the excellent talk. It's very impressive that you can write a Jax interpreter, 30-minute talk. And, yeah, we have some time for some questions. Bob,
I don't want to be the one raising my hand all the time. So does somebody else want to go?
I'm just floored. I feel like I didn't even know I had these questions and they got answered. That was wonderful.
Okay, I actually do have a question. So what happens if I do something like a transform where the dimensionality differs on either side? So in like Stan, our users have a lot of trouble figuring that out themselves. So if you take like a softmax transform where you like pin one of the values to 0, then you're going from n to n+1 dimensions. So can Oryx figure that out automatically, like to only do the slice of it?
Yeah, so there, yeah, as you suggest, there are essentially limitations to a direct like backwards interpreter or even the propagation interpreter, because the primitives in JAX may not be actually invertible. At least when you state it out of Jaxpr, you could get primitives in there that like you may not be able to invert because they've dropped some information.
Right.
So one thing Works does offer is kind of another level extensibility. You can decorate your own functions with the custom inverse and then write your own inverse and inverse log Jacobians. So that's essentially how you would implement something like a masked autoregressive flow, because those are really hard to invert just from Jaxpr. And the other alternative is you can write your own primitive and add it to the system. And now essentially you get another way to invert that function.
Yeah, I mean,
So,
that particular example, I could just write the function for the first n-1 dimensions and do it.
Exactly.
And presumably it would be able to handle that, and then the outside would be easy to code around.
Yeah.
The other thing I was going to ask is how complicated densities have you done? So like when Ben Goodrich was working out like the LKJ prior for correlation matrices, that came exactly this way. It came out of random matrix theory. There was an algorithm for actually generating random variables, and he just like worked out all the Jacobians from all those transforms to work out the density. Could you work out something that had like matrix operations and this kind of loops and that kind of stuff like that?
It is possible. Not everything is implemented yet, but certainly some matrix operations, if they're mathematically invertible, we could probably express it in Jaxpr.
Yeah.
One thing that's cool that I didn't showcase, I demonstrated that we can do functions with multiple variables, multiple inputs, multiple outputs. What I didn't demonstrate is that if you have, let's say, in like a real MVP flow, you'll take your input variable, you'll split it, you'll apply some invertible transformations, and you'll concatenate them back together. That's actually where this propagation approach really shines, because it can actually invert, split, and concatenate, which are essentially like logically splitting up information and joining it back together. So you may have incomplete information about the input at any given point in time, and it will understand when that is done. So it can actually do things like that as well, which maybe it's another kind of layer of complexity of programs you can write, where you split things and you combine them back together.
Thanks.
I have a question, maybe just to follow up to what Bob said, is what sort of functions are available in the primitives? Is there like a go-to like place in the code to like document this, like sine, cosine, log? Like I am curious, like what sort of weird things are available?
In general, like we're using like the set of core primitives that JAX ship with roughly mirror what NumPy has. So if you have like a, I don't know, numpy.log1p, JAX will also have a jax.numpy.log1p. It may break down into compositions of simpler primitives. There's actually not that many primitives in JAX compared to like number of functions in NumPy, but JAX mirrors all the functions in NumPy, so it's essentially a subset of those. In addition, Oryx is also adding primitives to the system. Specifically, it adds like it's taken TensorFlow probabilities distributions and registered those all as random variable primitives, basically. So you get the wealth of distributions in TFP as well as the JAX NumPy operations. So the complexity can grow quickly, but the core JAX primitives, there's actually not a ton of them. Yeah, look at jax.numpy to see exactly kind of what you can do.
Cool, thanks.
I have one question, maybe not related to the main topic here, but I saw very quickly you showed the just in time in JAX. So I was curious. So can you trick like cooperate with like just in time, or it's like separated, or we can do something like staging and we use both the interpreter and the just in time functionality in JAX?
Well, so what the JIT does in JAX, all it does is it hands off a lower level representation to XLA, which is a compiler, and XLA will compile it into, it'll apply optimizations like fusion, and XLA is really built for like machine learning, but it can be really handy in this case as well. JIT is essentially a no-op as far as semantics are concerned. So you can actually sprinkle it everywhere in Oryx, and you'll get a bunch of JITted functions. You can nest JITs inside each other, which will just essentially JIT the outermost one. But you could also JIT various parts of a program, and they should just kind of work with each other. It's not, I don't think personally it's doing anything super sophisticated, at least not from the JAX perspective. All the hard work is being done by XLA in that scenario.
Okay, thank you.